Okay, this should be good to go now. We'll see if we can make this work. For those of you who are not here in the room with us, the typical projector that we usually use in the center of this room is somewhere between dead and mostly dead. But it doesn't have any pockets, so we can't look for loose change. Oh, come on. Please, guys, come on. You do understand that I will give bonus questions on exams for quotes from The Princess Bride.
Okay.
The king's thinking son fired me. Okay. That's just horrible. Okay, so let's see what we can do with it. With that. Okay. That's about as good as we're going to get. Anybody have any questions? Oh, yeah. Right. We'll see if I answer them.
No. One question is just, can we go over the Makefile again, just to go over syntax? And then the other question is, when we compile, are we supposed to compile the phases separately? Because can we compile the phase 2 if we haven't actually made the header file already?
Okay, so, yeah, that's a good question.
Okay.
Now, you can do it either way. What you can do, you can have a rule that builds everything. And what that rule would have to do is it would have to have a rule for building phase 1, and then a rule for running phase 1, and then a rule for building phase 2, and then a rule for running phase 2. And just do it all. I'm fine if you do it that way, or if you want to just go ahead and put 2 separate rules, phase 1 and phase 2, where you run phase 1, or you run the rule to make phase 1, and then you assume that the user is responsible to run phase 1 to build the header file. And then you run the make file to make phase 2, and then the user is responsible for running phase 2. Okay? So either way you want to do it, but just in your write-up for the lab, tell me what you did. Okay? So, as you can see, I've got the notes up there, right, talking about the Makefile. So that was where I was going to start off today. So as soon as we finish addressing any other questions that people might have, I'll talk about Makefile. Yeah.
Just real quick, what do you want us to do with the failure or the success and failure as far as returning those values? We have a couple of functions we're supposed to return them.
Okay, are you talking about on the client side, or are you talking about on the module side? Who's the we? Are you we the client, or we the module?
Module, I imagine.
So if we are the module, then you have to make sure you return those parameters appropriately. So if everything went correctly, you return FIFO success. If something messed up, you return FIFO failure.
They're just going to be used more like, because really the only thing I did, like when you create it, if malloc returned null, so like it didn't have enough memory, that's when I did failure.
Really the only way I can screw up.
And then when you're removing it, the only thing I did is when the queue was empty, because I don't, any other time it would.
Yeah.
Because free doesn't return errors, does it? It just,
right.
If it's not there, then it doesn't do anything.
Right.
Okay. Just checking.
Okay. Other questions?
So
Button.
Are we doing anything with that in main, or are we just returning it?
So now the question is, what do we do with those flags on the client side?
Right.
It would be appropriate for you to check to see whether or not the module's behaving if you're the client code. Because again, we're assuming that you've got the client and the module separate, and there's this wall in between them. And even though you programmed them both, you're going to put one hat on when you're writing the client code and another hat on when you're writing the module code. So you've got to be paranoid on either side. So if you are the client implementer, you should check to see if the module is doing what it should have done by checking the return values that it specifies. Okay, and if it returns a FIFO failure on an operation it should have returned a success on, then you can do whatever you want to do in response to that. So like print out an error message saying, I'm dying, I'm melting. Or whatever other appropriate message you use. Other questions? My question is, how many processors does this little thing there have in it? Should we take it apart? That'd be fun. No questions? How many of y'all have made good progress on the lab? Anybody willing to admit they haven't started yet? Anybody haven't started yet? Anybody not willing to raise your hand? Raise your hand. Yeah, so you would cease to exist. You'd be a logical contradiction if you did that. Okay, so first things first, let us address one little logistical issue that might have a minor impact on your life. We are moving to EL 109 starting next class. Okay? I love this room. I think this room is much better, especially because it's got microphones and the students can push the buttons on the microphones and participate in the discussion. But there's a course held right now that is much bigger than this class, and they're having trouble fitting everybody in. So we're going to swap with them. Okay? So go to EL 109 next time. Please remember, I will also try to remember. So Dr. Chet Lowe will be teaching the class that will be in here. So if you come in and you see him, it's not a sub. You're in the wrong spot. Okay? All right. So if you remember last time we blasted through talking about makefiles. If you remember we talked about when we're building this program, we've got a lot of code, we've got a lot of instructions that we'd have to type in order to build it at the command line. So the instructions that we would have to enter is this GCC-C FIFO.C-O FIFO.O, similarly for FIFO main, and then this third instruction. What does this first command do? Does it make a program? Does it assemble? Does it create an object file? Does it do anything with FIFO main.c? Does it do something with FIFO.h? Yes, it does. Why? Because FIFO.c pound includes FIFO.h. Okay? -C means pre-process, compile, assemble, don't link. Stop after linking. -O says take your output file and name it whatever I'm going to tell you right here next to it. Okay, so we compile, assemble FIFO.c, compile and assemble FIFO main.c. What does this last statement do? Runs a linker. Okay? Are the only files that get linked together FIFO main.o and FIFO.o? Where's the implementation of printf? Standard, is it in stdio.h? How many of y'all think it's an stdio.h? So this is lab 0. Lab 1 is a nasty lab about a loader, and lab 2 is how does printf really work? And you will find that, yeah, it's not in stdio.h. It's in many files, and you will have to find all of them. Good stuff. Okay. So this runs the linker. You link FIFO main.o, FIFO.o, and you link against the standard libraries, the implementation of printf, the implementation of any other C runtime library functions you may access, like malloc. Okay? But that, you don't have to explicitly say that, because GCC understands that when you're going to link, I need to use the C runtime library. And so it'll do that automatically. You rename the output FIFO main.exe. You run it by saying /FIFO main.exe. Okay? And also note that all of this stuff applies to Linux as well. So if you're building a program on the command line under Linux, all this stuff is exactly the same except for the .exe. So Windows likes to have extensions on the ends of their programs. .exe tells Windows this is an executable program. Linux doesn't need to know .exe in order to know that it's an executable program. It just says this is a file, and if it has execute permissions, you can execute it. Okay. All right, so we don't want to type in those commands every single time, so we create a makefile. What is the syntax of a makefile? You have target, colon, a list of dependencies. Those dependencies are either files or other targets, okay? And then you have a set of rules. Rules, you have one rule on each line below here. As soon as you have a carriage return after a rule, that signifies the end of that grouping of rules, okay? You have to have a tab in from the left column, from column 1, into your rule. That tells make that this is a rule, not a target, okay? Okay, so how does this execute? Target is the name of something you want to build, or it's just a temporary string that you put in there in the makefile just to keep your makefile organized. What make does is it says when you say, I want to make this particular target, make will check your dependencies and see if your dependencies are up to date. If your dependencies are up to date, then it will run the rules. If your dependencies are not up to date, for each dependence that is not up to date, it will run the rule associated with that particular target. Okay? If you have a dependence that has no rule and does not correspond to a file, make will tell you, I don't know how to build this. Okay? So your dependencies either have to be files in your current working directory or they have to be targets in your makefile. Otherwise, make doesn't know what to do when you say this is something I depend on. It just assumes that you've got a mistake in your makefile. How does make check to see if something is up to date? If you depend on a particular file, so let's look at lab 0's makefile. Okay. So we start with this target called all. All depends on phase 1, and all has no rules. When you say make all, what this says is just go to the all target and see what it depends on and build everything that it depends on. There isn't anything else you have to do to build all in particular. And this is a convention. And I also figured out that I said to y'all last time, I said main, who was it? Was it you, Mitch, who called me on this one? Make doesn't look at all by default. All is just by convention the first thing you have in your file. So there's nothing magical about the all target. It's just by convention the thing that we use when we want to make everything. Okay? So all depends on phase 1. Phase 1 is not a file. Phase 1 is a target. Target is down here. So we have phase 1, colon. That depends on FIFO.o and FIFO main.o. These are files. They also happen to be targets. Because they are targets as well as files, make will go for the target part first. So it'll go through and look and see, I depend on FIFO.o. Is FIFO.o up to date? FIFO.o depends on FIFO.c. Okay, FIFO.o is a file. Let me check the write time of FIFO.o. And let me compare that to the write time of FIFO.c. If the write time of the source file is earlier, if I've updated this, since I've updated that, that means FIFO.o is not up to date, and I need to run the rule. If FIFO.c is up to date, that means its write time is earlier than the write time of the object file. I don't run the rule. Okay? So all I do is I build FIFO.o only if I need to, only if somebody's edited that file since the last time I built it. Okay? So I check this dependence, the dependence on FIFO.o, then I check the dependence on FIFO main.o. Execute those rules if they need to be run. Once the dependencies have been satisfied, I start to execute these rules. Then I check GCC. The rule just runs the GCC to do the link. And that's how I produce FIFO main.exe. Okay? So if you run make on here the very first time, it'll go through and build FIFO.o, FIFO main.o, and FIFO main.exe. If you then run make a second time, it will not build FIFO.o and FIFO main.o. Okay? Because those guys are already up to date. Okay. Questions about makefiles? This is not the first time, this is not the last time we will be looking at makefiles. We will have a large, nasty makefile for Lab 1 that we'll be going over probably in 2 class periods, yes.
How would you actually run?
Hit your button.
How would you run FIFO main.exe in the makefile?
Okay. You would have, in order to run FIFO main.exe in the makefile, what you would do right here, if you wanted to run it, if the user types make phase 1, and you wanted to not only build phase 1, but also run phase 1 at the same time, you would add a rule right here that would say /FIFO main.exe, and you'd supply the input parameters. The makefile would have to assume a name for what you want the input file to be. You'd probably say /FIFO main.exe in.text out.h or something. Data.h, code.h or something. Okay? Yeah.
I don't know if this would complicate or simplify people's lives, but the FIFO.0, you actually don't need targets for them because it has built-in rules to build them.
Yes.
I don't know.
But that does not serve to teach people makefiles. So there's a lot of magic stuff that can go on under the hood in makefiles. So if you, you know how to tell it which compiler you want to use? So there are some tricks on that. And if we want to use GCC, Eurolol's installation will probably end up using GCC because that's the only compiler available. But if you're on a native Linux build and you've installed your own version of GCC, if you just use the implicit rules that are built in, then life ain't going to be so kind to you. So stick to the basics. Life will make more sense. Yeah, Stephen.
If you leave off the all target at the first, will it just do the first target in there? What start?
Yeah.
Okay.
According to Mitch.
All right.
Other questions? Okay. I hope you're all at least getting comfortable with makefiles. We will now barrel on fast and furious into new topics. Because that's what we do in this class. By the way, those of you who have actually gone to the room where the lab is held have benefited from some introductory C material that I wrote up on the whiteboard. So, we are next going to talk about some more introductory material to real-time systems. I'm going to give you an answer to an exam question that will be on the final exam. I will give you a criterion for passing the class, or alternatively, a criterion for failing the class. And then we'll start talking about Lab 1. Okay? So, onward. Step number 1, what is a real-time system? But this class is called Real-Time Systems, and we haven't really talked much about real-time systems so far. I've just made you do this last FIFO programming assignment. Well, a real-time system is defined as follows: a computer-based system whose correctness depends not only on the logical result of computation, but also on the time at which the results are produced. Please feel free to memorize that word for word. I have almost every year asked an exam question that says, what is a real-time system? And oftentimes I get answers that may be valid but aren't my answer, and I ding a couple points and I get students that are mad. I'm putting you on notice. When I say, what is a real-time system, that's what I want you to tell me. Okay? If you don't tell me this, that's fine. It better make sense. If you don't know what a real-time system is, you're going to flunk the class. Pay attention. Write it down. Make sure you know. Not yet. Well, yeah, I think these ones are. Did I? No, I haven't put these ones up yet. They will be on the web. Okay. The other way to think about this is a real-time system is a computer-based system where you've got two things that are important. You need to have the right answer, and you need to have the answer at the right time. Okay? Time is a factor in the correctness of the program. Real-time system does not mean something that has to run really fast. This class is not about optimization of software. Want to talk about optimization of software, take the 5930 class, 3720 class, or whatever it's going to be end up numbered, probably 5720. That class talks about how you make software go faster. This class is not talking about how you make it go faster, but how you have software that depends on time as a factor of its correctness. You can have software that can execute very quickly, and as long as it completes in X amount of time, where X is a lot greater than it takes to run, things are correct, then everything's good. Oftentimes, software-based optimization is a factor in the development of real-time systems, simply because of the fact that sometimes the amount of work you've got to do and the time that you have to do it are very close, in which case you have to be very paranoid about how fast your software runs. Okay? Why is time so important to a real-time system? Because a real-time system interacts directly with its environment. Okay, we have a Mac computer here. We have other laptops kicking around the room. Those computers are designed to interact with you. Embedded computers do not interact with you. They interact with their environment. Now, you may make a counterpoint saying, well, what about a cell phone? The cell phone has an embedded computer. The artifact that we're talking about with embedded computers with cell phones is that they interact with RF signals. Okay? They sample those signals and extract voice from them and play it through a speaker to your ear. Yeah, they have buttons that you can dial up numbers and all of that, but there's a lot of other stuff that goes on under the hood. Embedded computer systems interact directly with their environment. An artifact of their interaction with their environment is the fact that they deal with and are governed by physics. One fortunate or unfortunate artifact of that is the fact that you have to respect physics when you're dealing with an embedded system, and physics will win. Sorry, gravity will work no matter how fast your code runs. So just remember that. Physics will win. Examples of real-time systems: an autonomous vehicle controller. So if you have a car that drives itself, if it is not sampling images, processing how far the road is or where the road's turning, if you're not processing those images fast enough, and the road turns faster than you're taking pictures, you keep driving straight and go off the road. Okay? You have to guarantee that you're snapping pictures and able to process those pictures fast enough so that you can detect when the road's turning so that your car will turn with it. Okay? Another example would be missile guidance software. So if you've got some software that's running on a missile that is intended to steer the missile towards an appropriate target, if you don't meet your deadlines in processing your IR images quickly enough, you end up hitting a bus, not a tank, which in most worlds, most areas, that's a bad thing. Okay. Cell phone. Cell phone is a real-time system because you need to encode voice at a proper rate or transmission quality. If you don't encode it at a proper rate, then your transmission quality will degrade and people won't be able to understand anything when you're talking on your cell phone. Okay, there's two classes of real-time systems. We classify them as hard real-time or soft real-time. Hard real-time are systems where it is imperative to the correctness of the system that all of its deadlines be met. You have to have a response within a specified deadline or the system will not work correctly at all. So you have to have real guarantees. Soft real-time systems are where response times are important to the correctness of the system, but there are times and situations where the system will function correctly if you occasionally miss a deadline. Okay? Now, if you read these two things carefully, it does not say what are the consequences of missing a deadline and how important are those consequences. The classification between hard and soft real-time systems is not based on importance or consequence. It's based on correctness. If the system functions correctly while occasionally missing a deadline, it's a soft real-time system. If it will never function correctly, if it misses a deadline, it's a hard real-time system. It just so happens that oftentimes safety-critical systems, missile guidance, anti-lock brakes, X-by-wire. X-by-wire is where you're doing drive-by-wire, steer-by-wire. Basically, you are replacing the traditional hydraulics in your vehicle with wires. So when you steer a motor, or when you steer your steering wheel in a car that has X-by-wire, which most of your cars don't, but you steer this way, what you have is sensors that detect your rotation on the steering wheel, and then that conveys through wires down to a computer at the wheels, and those trigger actuators which say, okay, turn the wheels. You don't have this hydraulic line or the rack and pinion that when you push on the brakes causes the brake pedals to be adjusted, or when you turn the steering wheel causes the wheels to be adjusted. So it's, X-by-wire seeks to remove the physical connection between the controls of the automobile exposed to the user and the actual artifacts that control the vehicle. X-by-wire, missile guidance, anti-lock brakes, nuclear power controller, those are examples of systems that are hard real-time. They are also examples of systems that have high consequence if you get it wrong. So there isn't a good example amongst those that say, okay, you can have a system that doesn't have a whole lot of, if it messes up, importance level is low, but it's still hard real-time. But examples of those systems do exist. Example, soft real-time systems, satellite data link, and Ethernet, just-in-time manufacturing. Let me ask you this much. What about a clock? Is a clock a soft real-time or a hard real-time? Okay, so if you have a clock that, if it doesn't tell time correctly or if it doesn't manage time correctly, is that a correct clock? You want that clock around? How many of you all have atomic clocks that you depend on regularly? You know what an atomic clock is? So, are the clocks that we use from day to day accurate or inaccurate? What about the clock you hang on your wall? And it's double hands, depends on AA battery, tick, 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 tick. Inaccurate? Are they okay for you to use? Okay, so is it functioning correctly if it's inaccurate? Is its correctness affected by its inaccuracy? We have to have a term that defines what is correct enough. What is the role in which that thing plays? You certainly don't want to use one of those wall clocks to measure how close Michael Phelps is to the wall when he's in the Olympics. Right? If you're differing by 100th of a second, you don't have the resolution on one of those clocks to tell the difference. You certainly don't want to measure nanoseconds with one of those clocks. But for the typical application in which that clock is intended to be used, it's accurate enough. So, what's the answer? Are clocks soft real-time or hard real-time? It depends on how you're using the clock. It doesn't depend on the clock. It depends on what you're going to use the clock for. Okay? So there are clocks whose intended use are hard real-time. There are clocks whose intended use implies that they're soft real-time. So a little bit of both. How about a shoe? That was an exam question I asked my first year teaching this class. Is a shoe a hard real-time or a hard real-time system or a soft real-time system? Okay, so Derek's saying it depends on what you use it for. Give me an example. Can you give me an example of how you can use a shoe in a context which requires it to be a hard real-time system?
Like if you work in an environment that requires has chemicals or like oil.
So like if you had to have like a one of those oil suits that are oil resistant, then it has to be that.
Okay,
For
so
safety maybe.
its properties have to hold up, and it's required that those properties hold up. But one of those properties that you mentioned, so I agree with the line of thinking you're saying, that the shoe is designed a certain way, and the features that the shoe has have to hold up in order for it to function correctly if you're doing something like an oil rig. However, is one of those features time? The answer is something like no or heck no. Okay? Sometimes I ask you non-obvious questions. Sometimes I ask you obvious questions. No, shoe doesn't have anything to do with a real-time system. How is a raven like a writing desk? Okay, just remember, the distinction between soft real-time and hard real-time is not based on consequence. Rather, it's based on the correctness of the functioning of the system. The reason why a shoe isn't a hard real-time or a soft real-time is that the correctness of the implementation of the shoe doesn't depend on timing deadlines. It has nothing to do with time. Okay? All right. A real-time system is usually, but not always, an embedded computer system. So we're going to talk for a minute about what is an embedded computer system. An embedded system is a computer-based system which interacts directly with its environment. Nothing there saying about time. You can have embedded systems which are not real-time systems. You can have embedded systems which are real-time systems. We typically deal with real-time embedded systems in this class. Okay. So here's a diagram of an embedded system. You've got a BDH and an ECS, where your BDH is a big dumb hardware. An ECS is an embedded computer system. These two interact with each other. This one talks to that one talks to this one. What do we mean talk? Well, they send messages back and forth in various ways, but this is typically how it's done. So you have your embedded system here, which has some A to D converter on it. You have some physical phenomenon over here. That physical phenomenon is sensed with a sensor. A sensor is a device that converts a physical phenomenon of some sort into an electrical phenomenon of some sort. You then convert that electrical phenomenon of some sort into a digital signal using an analog to digital converter. That digital signal is then captured and analyzed or done something with some computation inside your embedded system. You have control system going on, or signal processing, real-time data analysis, or logging, compression, encryption, a whole bunch of other topics that are dealt with in other classes. Okay? It decides something of what to do, or it decides something of an output. It outputs a digital word that goes to a digital analog to analog converter. That digital to analog converter is then converting that digital signal into an electrical signal. That electrical signal can then be applied to a device which converts electrical phenomena into physical phenomena. Okay, that is called an actuator. Some types of actuators take some electrical signal and convert it into something that pushes. Sometimes it converts it into rotation. Sometimes it converts it into sound. A speaker, for example, or maybe Derek's leg. So you have a speaker which will take an electrical signal, an analog electrical signal, and convert that into a physical signal, which is a sound wave. Okay? So you have sensors and actuators, digital analog converters, analog to digital converters. All of those form part of the embedded system. Okay? The physical phenomena that you receive and that you send are typically produced and consumed by your big dumb hardware. Okay? Your embedded computer system can also support a user interface, database, display drivers, console, I/O, lots of different stuff. Okay, so let's talk about general characteristics of a real-time system. They are typically large and complex. Think aircraft carrier. How many computers are on an aircraft carrier? Thousands. Okay? They're very complex. A lot of those computers are desktop computers, but a whole lot of them are embedded computers. Okay? Real-time systems need to deal with the real world. Applications and application scenarios evolve, and then the requirements of your embedded system evolve. Okay? So they are large, they are complex. Not every embedded system is large. And how do we classify large? Do we classify it as number of processors? Do we classify it as number of computers? Do we classify it as number of people interacting with it? Do we classify it as number of lines of code? Any, all, or none of those characteristics apply. But the point is, it's harder to program typically than when you're writing, say, Microsoft Word, or you're writing a typical desktop application. It's just hard to do. It's harder to get right. Okay? They have to deal with reality. Close enough only counts in horseshoes and hand grenades. Okay? So we have to deal with reality. We have to make sure that the embedded system gets the answer correct. Okay? You can have approximate control algorithms. They can lead to errors. Those errors can lead to inappropriate control, can cause crashes with real systems. You have to have controllers that increase in complexity to compensate for that. Those types of controllers, the complexity of the controller, you end up deploying that on your embedded system. Everything just spirals up and leads to more and more complex systems. Okay? So the idea that you have large, complex systems and they deal with reality, all of that just leads to increasing complexity. Reliability. Embedded systems are typically have to deal directly with reliability. For example, life support systems run by computers must be reliable. You also have high consequence systems such as nuclear power, car brakes, missiles, etc. Okay? You have to deal explicitly with reliability. You have to know whether or not your system is reliable. How many of you have ever written a program that you can say is reliable? How many of you have ever written a program that you know is not reliable? For those of you who say, so Mitch, I'm going to put you on the spot here, you can raise your hand. You said you wrote a program that you know was reliable. How did you quantify the reliability of your program?
I did the same thing every time, which I deemed to be correct.
You tested your program and it worked. How does that quantify reliability?
By definition of the word reliability.
What is the definition of the word reliability?
It does the correct thing every time.
The likelihood that the system will not fail. It's a measure of probability. What probabilistic analyses did you do on your program?
I tested.
Did you quantify what the mean time to failure was for it?
No, because it has.
Did you calculate how likely it would be to fail under certain scenarios?
No.
A debugged program is not necessarily a reliable program. So Hello World was the program that he wrote. He deemed reliable. Did you use Java? Reliability is a measure of success at which a program will run. It is not something, is it reliable or is it not? It's a measure. You have to quantify reliability. We have to deal with, and we're not going to deal with reliability so much because we've got a whole lot of stuff that we've got to deal with before we can actually start to address that topic. You got to think about that as a measure of probability that a system will work correctly. Concurrency. Oftentimes, systems have to implement concurrency in order to work correctly. Embedded systems, the real world, lots of things are going on at once. Okay? Embedded systems that are designed to interact with the real world have to deal with concurrency because there's so many things going on in the real world that they have to deal with. So humans think sequentially. Computers have the ability to deal with concurrency. The challenge is, how do you, Mr. Programmer, who thinks sequentially by nature, implement a program which is concurrent by nature, and how do you make it work right? And how do you test to make sure that it works right? You're going to gain a big appreciation of concurrency by the end of this class. Or abhorrence, one of the two. Embedded systems typically have tight constraints. Those constraints require highly efficient implementation. This is like what I was saying when we talk about real-time systems. You have to do a certain amount of things in a certain amount of time. When the time that it takes you to do the things that you've got to do is very close to the amount of time in which you have to do them, you had better make sure that your implementation is highly efficient, because we don't like pushing the boundaries. We have to have customized implementations very often when we're dealing with embedded systems with tight constraints. Those constraints often impose the requirement to have customized board, chips, drivers, operating systems, algorithms. Sometimes it requires customization all the way across the software and hardware stack. That's just the fact of how life is, and because of that, that's why we have to peel back all the layers of the onion. That's why you have to know all the layers of the operating system stack, the application, all the way up and down, so that we can understand when do we need to customize, tweak, debug, etc. Okay, so how do we develop an embedded system? So we are theoretically engineers. How do we engineer an embedded system? Well, you start with a system that kind of looks like this, where you've got a host and a target. The target is some board that you're using as your deployment. This is what you're going to use for your board, your chip, for your embedded system. You're going to deploy it using this platform. Okay? We have a host machine that is your regular old dumb PC or Windows machine, Mac, whatever you want to use. We have some interface from your host to your target. So your host is your PC, your target is your board, your interface, that's how you talk to your board. How do we talk to our board in this class? RS-232. Other interfaces are possible. Why do we need to have a host? Well, you remember that board that I showed you the other day? Did it have a monitor? Did it have a keyboard? How do you get stuff to it? You can't directly observe what the board is doing. You can't directly manipulate what's going on the board. You have to indirectly do those things. The way that we develop our program, we have to use the host computer, which has a keyboard, a mouse, and a monitor. That way we can type. So the host computer is to facilitate the editing and the development of your code that you're going to run on your board. So your host is to provide the build, debug, visualization environment to approximate regular program development. So here's a couple figures here that aren't going to fit on the page. Come on. There we go. Okay, regular development. This is just that same diagram that I showed you last time, but drawn vertically. You got your source files, preprocessor, compile, assemble. That applies to each one of the source files that you're using. Then you link, you have libraries, you execute. After you're done executing, you observe the behavior of the program and you modify your source files. Okay? So that's what we call regular development. That's the desktop development environment that you guys have been used to, you've been using all this time. For embedded development, when we're targeting a board, you have your source files up here. You have a preprocessor, cross-compiler, cross-assembler, cross-linker. These are compiler tools that are developed that target the processor board you're going to use for your embedded system, but they don't run on that processor. So normally you have a compiler that you sit in front of. That compiler, you type in your C program, you compile your code, that compiler runs on this processor. The program that results from the compilation process runs on this processor. A cross-compiler, the compiler tool runs on one processor. The executable that the compilation tools produce run on a different processor. Okay? So we are going to run compiler tools on your PC, on your host. They will produce a program, but you can't run that program on the host because it's going to target the processor on your board. Those two processors are different. They have different assembly languages, different machine languages. So we use a cross-compiler tool chain on the host processor, and we will have to deliver the executable down to the target. How do we deliver the executable down to the target? We use what we call a loader. So we have a host loader. This is however you talk to whatever interface you're using on your embedded system. Okay? So we're using RS-232, so we're going to have some software that interacts with a device driver that runs under Windows that talks to the RS-232 cable that allows us to download stuff to the target. So right here, the line in between host loader and target loader is our interface. Okay? On this interface, that's the actual wire that connects you down to your target. We have a target side loader, which is a software that understands how to talk to its side of the interface. You get the data and put it where it's supposed to go. Then we execute. What do we do when we execute? Over here, when we execute, we watch the screen, we look at printouts, we look at log files. Well, you don't have a hard disk over here. You don't have a monitor over here. You don't really have any way of observing what the thing's doing. So what do? You watch LEDs. See little blinky lights. And if the little blinky lights are doing what they're supposed to be doing, great. If they're not, then you go back all the way back up to the top. You edit your source code, tweak things, change things, go for it. Now, it's not as bad as you're just debugging by LEDs, but that's effectively the level of tools that we have. Okay. Cross-compiler, cross-assembler, cross-linker, those are utilities which execute on the host, but produce files that target the target board. Okay, the name of our cross-compiler is ARM-ELF GCC. It is a port of the GNU compiler collection, just the C compiler part of the GNU compiler collection. ELF is a file format that's output by the linker. ARM is the name of the chip that we're targeting. So it is a cross-compiler that is a port of GCC that targets the ARM and produces ELF executable files. Okay? I'm going to give you the cross-compiler via Blackboard. The cross-compiler that I give you works for Siglin on a Windows machine. It does not work for Linux. If you are going to be the type that wants to be a Linux guru and feels dirty every time you touch a Windows machine and you refuse to touch a Windows machine, I'm okay with that. So you're going to have to build your own cross-compiler. I can help you do it. You're going to have to build your own cross compiler, your own loader. And students have done that in the past. So if you want to go down that path, talk to me and I'll give you the resources you need to do it. But the least pain path is just using the tools that I've been giving you. Why do we need a host side of the loader and a target side of the loader? We need to get the cross-compiled executable from the host file system onto the target. The host target interface is the mechanism for the transfer, so we have to have software that talks to the hardware that does the transfer. Okay? What is the interface that we could use? You could theoretically use like a USB stick or an Ethernet. You could program a compact flash card if your board has a compact flash card reader, which ours happens to have. But because of the fact we use RS-232, you don't have to program one thing and plug it in and do something else. Those of you y'all have had 3710, right? Those of you who aren't grad students, you know the pain and suffering of that thing by programming EPROMs. So we aren't programming EPROMs. We have a way that we can program our board just by a serial cable. Okay. The algorithm for the host loader is as follows. Open the executable binary file. This is the target. So this is a program that runs on the host. We're going to pass to it the binary implementation of the target program. Okay? So we've got a loader program that's going to receive and open a different program, the cross-compiled executable program for the target. So we'll open up the binary file of the executable targeting the target on the host. Open up a device handle for RS-232. So this is how we're going to talk to the RS-232 port. Then for each packet in the executable binary file, we'll send the packet, then wait to make sure that the target has received that packet, then send another packet, then send another packet, then send another packet, and we're done. We'll say that we're done. On the target side, we'll figure out what the start address is, the start address of where we want to load the program that we're loading. And so while we're not done, get a packet from the input interface, 1 byte at a time, copy it to the start address, incrementing the start address. So we're just basically taking a program that gets loaded that gets built on the host side. We're going to take that guy byte by byte and copy it into memory on the target byte by byte. As soon as we're done, we jump to the start address and start running the target program. Okay, so I'm going to leave off there, and we'll talk some more about this stuff next time. But just as a preview, Lab 1 is you're going to be tweaking these loaders, the host side and target side loaders. Okay, we're going to implement some data compression on the executable that we're loading. Make sure you get Lab 0 done. I am in my office this afternoon, starting at 2:30.
Brad. Question, but are you